We will start in a minute, and I'm just gonna share the stream to my Discord server. Hello, everyone. Thank you very much for joining the stream. So actually today is gonna be our last live stream until next Friday because I have some other real life priorities that requires my attention. So I figured if I still keep doing this while busy with real life, I get burnout rather easily. So I figured we'll take a pause, okay? And quite frankly, there's a lot to walk through anyway, given the intensity we've been doing these live streams. So today is going to be a great day. So today we will walk through the derivation of the celebrated Fokker-Planck equation and Master's equation at the same time. And hopefully we'll see some of the connections between a stochastic differential equation and PDEs. Okay, so this is going to be a very exciting one. So we remember how we started. Okay, so we started from a historical review of the pioneering work did by Einstein, Langevin, and Ornstein-Uhlenbeck, and also Shmulachowski. These four individuals. So Brownian motion originated as an empirical phenomenon, right? The irregular movement, apparently random movement of a pollen grain in in water, basically. So, for a long period of time, the origin of its motion was unexplained, and physicists don't have a good model for modeling, for explaining the behavior of Brownian motion. So Einstein, I think the first breakthrough was due to Einstein. Einstein connected Brownian motion to the celebrated diffusion equation. Okay, and from there, he derived that the standard deviation for the displacement of the Brownian motion is is proportional to the square root of time. Okay, for some appropriately chosen time scale. Okay, this is critical. Okay, and Langevin, on the other hand, took a different approach. Langevin modeled the dynamics. So Einstein's work was a purely kinematic one. Einstein did not investigate the origin. So Einstein did not explain the origin of Brownian motion. It's simply a kinematic description. Langevin, however, considered the dynamics, that is the cause of Brownian motion, in what is now known as the Langevin equation, not perhaps, but definitely the first stochastic differential equation, SDE. Okay, and then later on, these methods get more widely adopted to model all sorts of stochastic phenomena, not just in physics, but also in finance and engineering. And actually, um, when I come back, which I mean, it's not a terribly long break anyway. It's a week break. So when I come back, our follow-up series would be stochastic process, on stochastic process for engineering. So right now we're doing stochastic process for physicists, and next up we'll do it for engineering. And the main theme would be filtering and control. And in the meantime, we will perhaps do a standalone series on Black-Scholes, okay? Because Black-Scholes is already pretty much is we have all the ingredients and the foundations for Black-Scholes anyway. So, and I'm not going to assume knowledge in the physics series. Okay, so these are pretty much kind of independent series. Stochastic process for physicists, stochastic process for finance, stochastic process for engineering. There's going to be some repetition, but with different focuses. So the problems are different, even though some of the mathematics do overlap. Okay, let's get started. Let's get to where we left off, because last time we attempted to derive the CK equation, not the CK equation, we have the CK equation. Last time we attempted to derive a master's equation, but due to time constraint, I didn't have time to explain some of the finer details. So let's start over. Okay, so let's start with the CK equation. This is a Chapman-Kolmogorov equation, which is essentially just the law of total probability. Okay, so it's not saying much on its own, but this governs all transition probabilities for Markov processes. So this is quite fundamental, and from that we will derive what's called a differential CK equation. So the differential CK equation is not standard terminology, unfortunately. There seems to be no common, like, universal terminology for this, so which is a bit of a shame. Okay, the name differential Chapman-Kolmogorov equation is termed by Gardner. Okay, so and differential Chapman-Kolmogorov equation includes Master's equation and the Fokker-Planck equation. It also, perhaps we don't have time to discuss this, but we will say that the differential Chapman-Kolmogorov equation actually also encapsulates deterministic process described by ODEs. So this further consolidates our claim earlier that Markov process is a generalization of ODEs and PDEs. Okay. Okay. Thank you very much. Thank you very much for your understanding, Steve. So let's get started. Okay. And of course, to get there, right, to get to the differential Chapman-Kolmogorov equation, we need some simplifying assumptions. And we'll walk through these assumptions rather carefully. And the mathematics, although rather involved, I mean, it's elementary. The mathematics looks kind of disgusting because of the complicated notations and lots of symbols to track, but it is not a difficult, so to say. It's an elementary operation. It's basically integration by part. I'll just put it this way. Okay, but the assumption is what matters. It looks rather involved, but with a little bit of patience, it's no problem to follow the mathematics. However, what's important is the underlying assumption. Okay, hi. Hi, Vizzy. Thanks very much for joining the stream. Okay, so warnings first. This is going to be a rather intense session, just like our last time. Okay, stochastic process in general is not an easy topic. It takes time, but it's doable. Let's go. Okay, differential. This is our main topic today. Differential CK equation. So first, let's recall what a CK equation is. What did it actually say? So in the CK equation, little f is the conditional probability density, or known as the transition probability density. So the meaning of little f is as follows. Given that at time t, at time t1, the stochastic process is at state x1. Okay, that's given information. Then at time t3, a future time, here. Then at time t3, the probability of the stochastic process being near x3, that is in the interval x3 plus dx, equals the density function f of x3 t3 given x1 t1 times the length dx. Right? It's just the usual interpretation of probability density. Okay, this function satisfies the CK equation. And the idea is for any intermediate time t2, okay, t2 can be any number between t1 to t3. The transitional probability density from x1 to x3 during the time interval t1 to t3 equals the integral of the transition density from x2 to x3, from the state x2 to the state x3 during the time interval t2 to t3. So that's f of x3 t3 given x2 t2. Okay, this is a transition density. The same function, it's just different argument. And then times another transition density, this time going from x1 to t1 during the interval, x1 to t2, x1, so what am I talking about? x1 to x2 during the time interval t1 to t2. It's perhaps more clear from the diagram. And the intermediate variable x2 is integrated over. And this is justified by the law of total probability. So the intermediate state is something of little interest. We can, but it has to be, the stochastic process, right, has to be something at time t2, has to be in some state x2 at time t2, which is an intermediate time. And for that, you can just integrate the nuisance variable, intermediate state, x2. So that's the CK equation. All right. So what we want is, a differential equation that describes the time evolution of the transition density. Okay, so you can think of what happens, right? What happens if T3 and T2 are close? Okay, what would be the time evolution in that small time period? And hopefully we can integrate that equation to get something that is more manageable, because CK equation on its own is very difficult to solve unless you're dealing with a very restricted scenario. And unfortunately, for most Markov processes in physics, the CK equation is unsolvable. Yeah, so we will have to make the following simplifying assumptions as follows. Assumptions. Okay, the first one says the following. It says P of, well, first write down the math and then we'll explain. Okay, if P of x t plus delta t given zt, we all know what this means. Okay, so from now on we'll be using P. Actually, why don't we just change it now from up here as well? We'll use P, okay, to use P to denote the density. Okay, so this quantity right here, so you see the time goes from t to t plus delta t. This equals a function w x given for w of x given zt times delta t plus little o of delta t. Little o of delta t just means higher order terms of delta t, such as delta t squared. And this is true for x minus z. Here x and z are vector arguments. So in general, the states can be vector valued. Right? You can imagine if we're trying to discuss Brownian motions in space, right? You would need vector arguments to denote positions, right? So x and z are vector argument. What is w and o here? W is a function. W is a function. This is a function, and little o is higher order term. Stands for higher order term. So little o of delta t just means that the function, the terms here, so a function f is little o of delta t. A function f of delta t is little o of delta t. It means that if it divides by delta t, the limit is 0. It means the following, okay? Because in writing, sometimes it's hard to distinguish little o versus big O, okay? It's easy if you, it's perhaps more transparent if you write it, so if you typeset it, okay? Little o, this is little o. Little o is the order notation. Is 0, okay? And this is true for x minus z modulus greater or equal to epsilon for all epsilon greater than 0. And the assumption is true, quote unquote, uniformly is true, quote unquote, uniformly for in all the variables x, z, and t. It just okay, so this is a rather involved expression. Let me explain. Okay, so let's draw a picture. Okay, let's draw a picture. So this is the state space, Rn, n-dimensional space. And here, z is the initial state at time t, right? So the stochastic process is at the point z at time t. So xi, the stochastic process, xi of t, our notation yesterday for the stochastic process, is at z. That's given. Okay, so now let's draw a little circle here, actually a sphere in ND. In case I need the n later, I'm going to use d for the dimension, okay, rd. All right, so here you have this circle, which is a small ball, okay, small ball with radius epsilon. So epsilon is a positive number. Epsilon is a positive number, and here it says, okay, x for x minus z greater or equal to epsilon. It means x is outside of this sphere. That's the future state, x is outside of this sphere. All right, and this transition probability equals some function. W is some function equals some function that can depend on x, z, and t, but not delta t. And then times delta t plus higher order terms of delta t. Okay, and the assumption uniformly. The word uniformly just means that. It just means that here this limit relation is true for all x, z, and t. Okay, this is not a rigorous definition of uniform convergence in analysis, but basically here you can think of there this expression, okay, this expression, the limit expression f of delta t over delta t, is bounded for all x, z, and t. X, Z, and T. So without getting into the details of uniform convergence, but basically this expression as delta t tends to 0, this is true for all x, Z, and t, and the expression is bounded for all x, Z, and t. Okay, this is a very rough description of uniform convergence. Okay, so that's the first assumption, but what does it mean physically? What is this W function about? Right, so which I think it deserves some explanation. This assumption is a statement about finite jumps, not infinitesimal jump. Okay, let me write it down. This assumption is about finite jump during small time interval. This assumption is about finite as opposed to infinitesimal. Jump during small time period. Okay, the best way to understand this is through a simple concrete example. Let's consider, for example, the Poisson process. And here's a crash course on Poisson process. For a Poisson process, okay, it is a continuous time stochastic process that takes non-negative integer values. So x of t is in 0, 1, is in 0, 1, 2, and so on. That's a Poisson process. This is a crash course on Poisson process. And the sample trajectory looks something like this. Okay. So I was talking about what is a Poisson process. Poisson process is this. Poisson process is view count for YouTuber. So think about how view count behaves. It jumps at finite time. At some finite instant, it jumps from, say, 0 to 1, and then 1 to 2, and then 2 to 3, and so on. So there is a small possibility for the view count to go up during a small time period. And that probability can be described by the rate function. So think about this. So the Poisson process, it goes up by 1 unit at a time. It can only go up 1 unit at a time. So this kind of process is called a counting process. So it goes from 0 to 1, and then 1 to 2, and then 2 to 3. It never goes down. Right? Just like in view count, it never goes down. Or hope it doesn't go down. Right? So the concurrent viewers, this can go down. The views will never go down. This is a Poisson process. This is a birth and death process. Right? The concurrent viewers, this is a birth and death process. It can go up or down. There's possibility of quote-unquote death. A viewer goes away. Right? So the views always go up, and that's the Poisson process. So here, at some point, at some random time, it goes from 0 to 1. Okay, and then it stays there, like one view, and then it goes up again. And it goes up, and then it goes up. Right, so that's the counting process. And the Poisson process is the simplest counting process. So what the Poisson process says is that, so given that the current state xt, x of t is n, where n is a natural number, 0, 1, non-negative integer. Okay, so that's the current state. At the next time instance, say t plus delta t, it either go up or stays constant. Right? These are the only two possibilities. So consider a small interval. This is t is x. Okay, consider a small interval. In each small interval, x of t either go up or stays constant. So the jump would be m plus 1. The jump size would be 1, right? So if it reaches m plus 1, that would be a jump. And the fundamental assumption about Poisson process is this is lambda, a constant, times delta t plus O delta t. That's the Poisson process. Okay, and from that you can immediately write down the probability for no transition during the same time interval. So if you start from x of t equals n, so in the next time instance t plus delta t, nothing happens. Right? The view count stays flat. The probability would be 1 minus lambda delta t plus O delta t. So this W function here is a constant for Poisson process. So assumption 1 is about finite jump. The jump size is 1. It's not infinitesimal. Okay? Doesn't matter how small you shrink the time interval, the jump size is minimum 1. And in fact, in a small time interval, we only allow a jump size of 1 to happen. So this is a more general statement than the Poisson process assumption. But the idea is the same. Okay. As for example, if we're talking about the concurrent viewers, then it will be a burst and death process. So you can, let's say x is now concurrent viewers, x of t may go up in the next time instance, or it may go down, right? So here in the equation, I would have to have another line say probability of x of t plus delta t equals m minus 1, given x of t equals n, is another constant, say mu times delta t. That will be the death rate. Mu times delta t plus higher order terms of delta t. Okay, let's predict, does it go up or down? Chat, what's your thought? Okay, let's try to flip a coin. Does this number go up or down in the next instance? I'm thinking it will go up. My bet is up. Okay, so I'll just put it here. I'll wait for something to happen while we comprehend this assumption. Yeah, it goes up, as I said. Yay! Awesome. Okay, so you see, so that's this assumption in action. A jump just happened from 7 to 8. Welcome to the stream. All right, so that's the first assumption. I hope this is clear. Okay, this function in general can depend on the initial and final state, the original state, and the new state it gets jumped to. Okay, we assume that for small interval delta t, this probability is linear in delta t. So and it's just a coefficient. This is just a proportionality constant. Okay. In general, you might have something called the inhomogeneous Poisson process. For example, here we're considering the Poisson process. Let's say, because right now it's kind of early, right? Early in the morning. Normal people have to go to work, in North America at least. Right. So, in that case, you might assume that the arrival rate is relatively low, right? But if, let's say, if I start the same stream on a Saturday morning, people are more free. So in that case, it will be higher lambda. The lambda will be higher. So lambda in general is a time-dependent function, and that's why here W in general depend on t. Okay, so that's the first assumption. It's about finite jump. I hope this assumption is clear, because what tends to happen in physics and stochastic modeling is that you start from making assumptions about these W's. Okay, so we did that in one of our PDE sessions, actually in our first PDE session, where we introduced the application of PDEs to a stochastic process. There we just wrote down this assumption for burst and death process for linear growth. In that case, the lambda is replaced by a constant lambda times n, a function that is linear in the current state. That's another example. Okay, perhaps we can find it. I'm sure we can find it. Here, this is, where's my YouTube thing? Yeah, there you go, PDE1. Right, this is the birth and death process. The stochastic process may go up or down. And each transition is a finite jump. It's not infinitesimal. Right? And here you have the fundamental assumptions. You got these transition rates here. Lambda n is the birth rate. Mu n is the death rate. Okay, for what we call a Malthus process, linear birth and death process. Lambda n, do we have that? Yeah, here, special case, Malthus or linear birth and death process. Lambda n is n times lambda. So you can think of lambda as the birth rate per capita, and mu n is the birth rate, is the death rate per capita. So you can see the W function, it depends on the current state, n, and also depends on the destination. If the next state is n plus 1, then the W function equals lambda n, which is n lambda. And in the opposite scenario where a death happened, then W function would be n times mu. Of course, there's other possibility. This one, it does not describe the W function. This one is not described W function because W function only described finite jump. Here, the final equation for no change, right, is just 1 minus these two probabilities, right? This is no jump, so this is not described by the W function. Just want to make that extra clear. W function only describes finite jump. And for the first two scenarios, a birth or death, a finite jump occurs. Okay, so now let's go back to our main assumption here. Okay, so the reason I spend so much time discussing this is because this isn't just some mathematical shenanigan. This is what you directly control if you're a modeler. Okay, this is W. W of this is W of n plus 1 given n. For all t is a constant lambda. I will only eventually stop working. Oh, hi Mela, thanks for joining the stream, although I'm not quite sure what you mean. Okay, so that's the first assumption about finite jump. Let me highlight that. So what would be a one-sentence description for W then? So you can think of W as the transition rate density. It tells us the instantaneous rate at which the process make a jump from z to x. Should we write it down? I think we should probably write it down, okay? So interpretation of W, I think that's important. Because this is something that, as I said, you directly have control of as a modeler. Okay, so here, W function. Yeah, so Vizzy, if you're still in the stream, this is the explanation of W. W is understood as the transition rate density. Some people like to call it the jump rate, which also makes sense because of what we just discussed. Okay, the jump is indicated by this. Okay, we're not considering infinitesimal transition. This is a jump. Okay, so for transition rate density, right? It tells us the instantaneous rate at which the process makes a jump from z to x. D to x, all right? So just to make this even more explicit, okay? Let's take a small region, namely, for a small region, say A, in RD, the probability here, we're just going to say, write something similar to the Poisson process assumption, right? So the probability of x of t plus delta t in this new region A, given that the initial state x of t is z, is what? Is approximately delta t times the integral over A, the w function, x given zt, and then dx. So that's why we call it the transition rate density. So when it comes to unit, right, when it comes to unit, w should have the unit of 1 over time over position. Okay, because probability has no unit, this is dimensionless. So the integral should have the unit of 1 over time, and w gets multiplied by the position, so w, the dimension, okay, this is the notation for dimension or generalized unit, is 1 over time times position. This can also be a good check for dimensionality. All right, so that's the assumption here, the first assumption. Okay, I think we can move on to the next assumption now. Okay, the next assumption says the following. Once again, we'll first write down the math, and then we'll do some interpretation. It says the following. It says, once again, for all epsilon greater than 0, epsilon is positive, the integral over the region x minus z, absolute value less than epsilon, so that's basically the inside of the sphere, inside the ball, the integral of dx, x is a vector. I'll stop writing vector signs, okay, because it's tedious. So dx times xi minus zi times the transition density, okay, transitional probability density, p of x at t plus delta t, the same function, okay, z t. So this equals, okay, this equals a function, another function a zt, another function zt plus little o epsilon. Oh, actually, I forgot the delta t. Little o of epsilon times delta t. Okay, so this is perhaps more complicated, and indeed it is. Indeed it is. So let's think about what this means. So in a nutshell, to describe this equation in one word, we're talking about drift. This equation talks about drift, and we'll explain why. This is a statement about drift, all right? Let me just write it down. Hang on. In short time interval. So far we introduced two functions. One is the W function that models the finite jump. The W function is the finite jump. And here you have a function A, which models quote-unquote drift. So what do we mean by that? Let's explain. So what is this integral on the left-hand side measuring? What is the integral on the left-hand side measuring? So if, let's say, if the initial state x of t is z, if this, let's say, the initial state, let's use xi, okay, xi, or x. Let's just use big X, okay? Let's use big X. So the left-hand side integral is this. So let's given the initial state x of t is z, and we're considering the displacement. We're considering the displacement. The displacement is x of t plus delta t minus x of t, obviously, which is x of t minus z. X of t plus delta t minus z. It's very Einsteinian. Can you say that? Einsteinian. Okay. Very Einstein way of looking at things. So x of t plus delta t, the displacement minus z. This is a vector, right? This is a vector, so its ith component, whose ith component is a subscript I. So this ith component is x with a subscript I. Okay. Guys, I'm not looking at chat right now. Okay, so I'm just going to finish this little presentation about assumption 2, and I'll come back for questions. Okay, so this is the ith component, and what's the integral? The integral on the left-hand side is just the average of the displacement. It's essentially just the expected ith displacement, except now you are only integrating over a small region. This is essentially the expected ith displacement except that we only count for outcomes for which you have the inequality x minus z modulus less than epsilon. Okay, if it's a true expected value, it should integrate over the whole of Rn. But here we're only integrating it over a small region. Okay, and okay, so that's the integral on the left-hand side. So what is the physical meaning of the left-hand side integral? Basically, it says during a small time interval delta t, small time interval with length delta t, what is the average displacement in the ith component? Right, considering the local motion near the current state. So therefore, the left-hand side integral, this is the average displacement in the ith direction. Consider average displacement during delta t, okay? In the ith direction, and considering local motion. near the current state. So this is an infinitesimal quantity, not a finite quantity. So the displacement is the average displacement is infinitesimal. It is proportional to the time interval, length. Okay, so that's the interpretation here. Current state is near the current state is z. Okay, so that's the meaning of the left-hand side integral. Right. So so this begs the question: why are we considering only why restrict, right, to this small region, x minus z absolute value, or x minus z length norm less than epsilon? Why do we do that? Right. This is motivated by the Brownian motion, because for Brownian motion, there's no finite jump. During Brownian motion, there's no finite jump. During small time interval, displacement only happens locally, overwhelmingly so. Think about the Brownian motion, right? The Brownian motion, you have Gaussian displacement, Gaussian distributed displacement with the standard deviation, or the variance, right? Or with the variance proportional to delta t. And actually, in Brownian motion, there is no drift, right? There is no drift in Brownian motion unless you add a force field to it, right? The analogy with Brownian motion is actually more appropriate if we discuss the second moment, actually, which will be the third assumption. But I'm just trying to explain, why do we only consider this small region? Because for a large class of stochastic processes, okay, during small period of time, only small transition can occur with overwhelming probability. Okay, so the previous assumption deal with finite jump, and here we're focusing on the local motion. So we're separating two types of behavior: local motion near z, and versus finite jump away from the z. Okay, so this is about local motion. And earlier we're talking about finite jump. Okay. Contrasting the Brownian motion versus Poisson process. The transitions are of different natures. Okay, so we separate those two behavior. And now let's come to the physical meaning of A, right? What's the physical meaning of A? Well, the physical meaning of A is now apparent, right? The equation 2, the assumption 2 says that the local average displacement in coordinate I over a short period of time, delta t, behaves like AI times delta t. And therefore, AI delta t, right, so AI, the function AI, is the instantaneous average velocity. So you can write this down. So A, the function big A, they look rather intimidating, right? This integral looks rather intimidating, but actually, if you later on, if you see a stochastic differential equation, A is readily available. Okay, now we're just giving it a physical interpretation. You'll never in practice need to actually calculate this horrendous looking integral. Okay, but so it's just a definitional thing. The AI. So AI is the instantaneous average velocity known as drift. It's a bulk motion. This is not diffusion. This is a bulk motion. So think about a flow in a pipe. That's a bulk motion as opposed to diffusion. Right? Diffusion is an example of diffusion would be drop ink into clear water. Right? We all know what that looks like. The motion has no bulk movement. It just diffuses in all directions. Drift, on the other hand, is directional. Right? So here AI is a component of a vector. If you put all the AIs together, you get a vector. It has a direction. This is instantaneous average velocity, aka drift, in the i's coordinate direction. Okay, in financial application, the drift would be a riskless interest rate. Okay, like the U.S. Treasury rate, which is widely considered as nearly riskless. Right. So if that's a deterministic growth. So AI is an instantaneous average velocity, aka drift in the i's coordinate direction at state z and at time t. So that's the interpretation of this quantity. And you can sort of think of it as the limit as delta t tends to 0. The expected value, let's use a physicist notation for expected value. Okay, use the angle bracket, because after all, this is a series for a physicist. Let's use the physics notation. It's the average of what? Of xi of t plus delta t minus xi of t with the condition, and physicists typically write the conditioning as a subscript for the angle bracket. X of t is z. So that's the average of the i's component of the displacement divided by delta t, given that the current state is z. Hopefully we're clear about this. Okay, so I was saying that AI is just a component. If you put them together, you get a drift vector field. And as a result, a vector zt, which consists of components a1 all the way to ad, each of them may depend on z and t. This is a drift vector field. Okay. Yeah, hopefully this is clear. So of course here, obviously, as we said earlier, actually we should put a minus approximate equal sign, because we're only considering the integral. If the integral is over the entire RD, then you literally have this equation. But here we're only considering the integral over a small region. It produces an error, right? And the error is of the order of O epsilon. And this is also, we assume this is also uniform in the sense that, okay, and we also, we assume this is uniform in the sense that the proportionality constant omitted in the O notation is bounded for x, z, and t. Okay, so let me just also explain that a little bit. So this assumption is uniform, because this is, I mean, why do we make this sort of assumption? Well, because we need it later. We make these assumptions to cook up results down the road, basically. Uniform in z, epsilon, and t. Okay, so what do we mean by that? What do we mean by that? Well, I'll finish explaining that. I'll come back to chat, okay? Sorry, guys. Okay. This is uniform. The part uniform in z, epsilon, and t means the following. Means if you consider the error, which we grouped here as a O epsilon term, it will be something like this. Okay, it will be something like this. So it means the integral over x minus z absolute value less than epsilon xi minus zi p blah blah blah. So writing this is tedious, but basically this is the integral minus the dominant term on the right hand side. That's the ai times delta t. This thing minus ai delta t will have an error, right? We'll have an error. That's the remainder term. The remainder term, the uniform assumption is about this remainder term. The remainder term in general it depends on delta t, z, epsilon, and t. Okay, and means the remainder term ri. Okay, ri, which in general depend on these variables, has a bound. This has a bound of the form c times epsilon. That is linear in epsilon because of O epsilon. And the proportionality constant, which is suppressed in the little o in the big O notation, in the big O, the proportionality constant c is omitted in the big O notation, is bounded. Is bounded for all z, epsilon, and t. That's it. So the O epsilon is a uniform spatial error. That is to say, we don't allow c is a constant. Basically, that's basically mean that i.e. we don't allow, for example, ri absolute value to be less than or equal to c zt. Okay, I'm trying to avoid making this into a full-blown real analysis lecture. So the point is that this coefficient here is a constant. This is a constant, and this c here, we don't allow this situation where c z of t becomes uncontrollable, where it becomes arbitrarily large as the z or t varies. We don't allow that. Okay, does that make sense? Or t varies. That's the assumption. Once again, why do we make these a seemingly arbitrary assumption? Because later on when we do integration, we want to interchange order, and this is just a nice setup. Okay. Because in a Chapman-Kolmogorov equation, we need to do integrals, and we're integrating all over, as we said, in a CK equation, it involves integrating all the possible intermediate states. Right? The intermediate state, we want the estimate, okay? We want the estimate here to remain valid as z varies. Okay, so that's the reason why we introduce this uniform assumption. So the uniformity in T, uniformity means that the assumption doesn't deteriorate as you vary z, t, and epsilon. Okay, so hopefully that clarifies things a little bit. Okay, yeah, perhaps we can use a shorter description for AI. AI is the local deterministic drift. Right? So AI, so in short, AI is the local deterministic drift. I think I'm starting to sound like a broken record. But my point is, because this is a series for physicists, I try to make things as physical as possible. These functions has modeling significance. Okay, and if you know a little bit of a stochastic differential equation, here, if you know a little bit of a stochastic differential equation, you can consider this, okay? Although I don't assume SDE already. I had a session on SDE on the 15th, but basically, if you consider dx of t equals a of tx of t dt, this on its own is the ordinary differential equation. And that's just the time derivative for x. But for SDE, you also have a drift term, okay, called sigma. Usually that's a mu. Okay, the drift term is mu in SDE. Mu of t x of t plus sigma t and x of t times dw of t. dw of t is the increment in the Wiener process, mathematical Brownian motion. Okay. So this will be the drift. So for example, if you're given a stochastic differential equation, you can immediately recognize what the drift is. Okay, but here, because we're discussing this assumption in a general context for Markov process, this explanation is perhaps a little bit more complicated, right? So here, in the stochastic differential equation, the drift is instantly recognizable. But this is what drift means in a general Markov process context. Okay, the SDE interpreted in an Ito sense, right, if you understand what that means. I'm not going to make this into a full-blown lecture on stochastic calculus. So if you know what an Ito SDE means, by the way, you can check out the video on Ito's lemma on the channel. Ito's lemma, which is in the stochastic calculus series, and there I explain what an Ito SDE means. So if this is an Ito SDE, then the drift is immediately available, basically. Okay, so time for chat. Does everyone leave? Okay, because of the horrendously long explanation. Oh, hi Christian, thank you very much for joining the stream. Dimension analysis, very physicist coded. Yeah. Needs sequential Monte Carlo adapted to high dimensional space. Okay, this is still very broad. I'm not quite sure what that means. Levy process, CDL, DW, and SDL Levy. Well, we're still dealing with DW here. Right? Levy process is the generalization of Brownian motion and Poisson process. Okay. Hence, watching to catch the upcoming filtering seminar. Yeah. You're very much welcome. So here we aren't going to be talking too much about, I mean, if at all, about filtering in this session. We're trying to derive the Fokker-Planck equation, Fokker-Planck equation and master equation simultaneously. That's our main goal. Still, like an hour. We spent an hour. We still haven't finished discussing the assumptions. Hopefully my effort pays off, okay? Because I don't want this to be an axiom pushing mathematical game. I want to make sure that every quantity we introduce is well understood. Every assumption that we introduce is well understood. Because the whole point of the channel, because despite we're doing applied mathematics, you're unlikely to see a single line of code or package. Because I want to focus things on the fundamentals. Okay, make sure we know what we're dealing with before touching the digital form. Okay, this is the meaning of the second assumption. All right, so next up. So we have jump and we have drift, and now it's finally time for diffusion. Okay, what does the assumption about diffusion say? And here's what it says. Okay, so let me pull out the second assumption here. Assumption 3. If you understand assumption 2, then assumption 3 is relatively easier. So it says, still, you're dealing with an analogous looking integral. The integral of x minus z, absolute value less than epsilon, dx, xi minus zi, times xj minus zj, okay, times the transition probability P of x t plus delta t given zt. This is another function called bij. So this is a matrix element. Bij zt plus O epsilon once again. And once again, this is uniform in z, epsilon, and t. This is uniform in epsilon, z, and t. And this similar interpretation as the same interpretation. Okay, same interpretation means that if you consider the remainder term has a bound of a constant times epsilon. The constant works for all the other variables. All right, so that's it. Okay, so what's the meaning of this one? What's the meaning of this one? So it looks like a second moment, isn't it? It looks like a second moment, right? Here, earlier we can only consider the first moment. Here we're only considering the second moment. But once again, it's not quite exactly the second moment because we're only integrating it over a small region. Only integrating a small region, and the error for not including the outside of the sphere, the ball, is of order O epsilon. Okay, so let's now write down the definition for B, interpretation for B. Okay, so what does this mean? So what does the integral represent? The left-hand side integral interpretation. So here delta x is, let's write delta x, the displacement, as x of t plus delta t minus z. Okay, and here the integral is essentially what? The integral is essentially but not literally, due to the limited range of integration, is essentially the average of delta x I times delta xj, given that x of t is z. It's basically the second moment, except that we're restricting ourselves to the local region. Except that we are restricting ourselves to the local region. X minus z length less than epsilon. So it measures the second moment of short time displacement. So therefore, the left-hand side integral is approximately the second moment of short time displacement. Okay, so here it tells us about the size and correlation of fluctuations. The size and correlation of fluctuations in different coordinate directions. So the quantity, the second moment, it measures the size and correlation, because of when I and j are not the same, you measure the correlation. It's like a covariance, size and correlation of the fluctuation. In different coordinate. Direction. Okay, i.e. the strength of the diffusion. The strength, this is a local diffusion matrix. So Bij is the local diffusion matrix. Or if you really want to sound fancy, you can call it the diffusion tensor. Is the local diffusion matrix / tensor. So for drift, you need a vector. For diffusion, you need a tensor or a matrix, because of the covariance structure. Okay, so is actually it should be Bij times delta t. Bij on its own is the rate of change, the rate of growth of the second moment. Bij times delta t is the local diffusion matrix, local diffusion tensor in short time. So that's the interpretation of this quantity here. So I want you to bring your attention to our first episode. Okay, here's the note: stochastic process for physicists, where we examine the derivation for Einstein. Because really what we're doing is just redoing Einstein's analysis on Brownian motion, but in a more generalized context. Here, not this one, not this one. Okay, going back. Here, yeah, this one right here. How did we get to the diffusion equation for Einstein in Einstein's paper? Okay, we started by assuming the displacement function, the displacement density phi of delta, to making assumptions about a phi of delta. So here, you see, phi is assumed to be normalized because that's a density, has a mean of 0 because there's no bulk motion, and the second moment, actually half second moment of delta divided by tau. Tau is the finite short, right, but finite, not infinitesimal, okay, short but finite duration that Einstein considered. This is the Einstein's time scale. So you see, this is second moment per time, and turns out to be the diffusion coefficient d. Right. After solving the heat equation through Fourier transform, which we did not do, we will do so in our PDE session. You see, but what's important is this definition of d, and d turns out to govern the second moment growth. Here, standard deviation is square root of 2 dt. This is d. D is the displacement second moment relative to time, the rate of change of the displacement second moment relative to time. And here we're doing this in a more generalized way. Here we're considering multidimensional motion. Oh, I forgot times delta t. My bad. There should be a times delta t here. All right, so that's it. Okay, so Bij is the instantaneous growth of the second displacement moment. Okay, so if we come back and let's look at an example. Once again, I'm going to use SDE as an example. It's okay if you don't know SDE, but if you do, I think this will be helpful. So here, let's consider SDE in the ith component. dxi equals ai dt. ai may depend on x and t in general, and then plus sigma I dwi. So let's say this is a simple example. Okay, this is a simple example for where we're trying to contextualize this definition. What is B in this case? What is Bij in this case? Well, you can just calculate. First of all, you can calculate. Let's write it in a finite difference format. Delta xi is approximately ai times delta t plus sigma I delta wi. The finite approximation, and you can calculate. You can calculate the delta wi, because remember remember the mean of delta wi is 0. Brownian motion has 0 mean displacement, and here the covariance function delta wi times delta wj. This is Kronecker delta times delta t. Right. Remember, the variance of delta wi is proportional to delta t, and when I and j are not the same, it's just they're independent, so it's 0. So that's why you use the Kronecker delta here. All right. So from there you can calculate the average of delta xi and delta xj. Let's calculate that. So what's that? Delta xi, let's multiply. Okay, so you have ai delta t plus sigma I delta wi times aj delta t plus sigma j delta wj. So all the first order term would vanish due to this thing, due to 0 mean of Brownian motion. So you get the average of AIAJ times, oh, actually you need a delta t square. This is the deterministic motion. I'm not saying this is a covariance, right? This is the second moment. So this is uncentralized second moment. You still have this term, and the linear term will cancel. For example, ai delta t times sigma j delta wi. That's the first moment in wi, so it cancels. Well, actually, you know what? You don't even need. Actually, yeah, you do need that, because ai aj can depend on x, so these are random as well. So there's random. You need the sign. You need the average sign here. Okay, so that's no problem. And finally, you have what? You have the you have here. Oh, actually, this is, even though this is non-zero, but this can be ignored. This can be the second highest. This is second order moment. This is second. This is the second order infinitesimal. This is ignorable. Okay, and then plus what? Plus the a linear term in delta t. So this will be sigma I, sigma j, and then you have the average of delta wi times delta wj. So that's a Kronecker delta ij times delta t. So you see, this is much larger than the first term, so this is ignorable. So pretty much you can just say this is approximately sigma I, sigma j times delta ij delta t. And this is your Bij here. Therefore, the Bij earlier in our definition is sigma I times sigma j times the Kronecker delta ij. Okay, so this is a concrete example of how to obtain B. Okay? So hopefully this is clear. B is the local diffusion, B times delta t is a local diffusion matrix slash diffusion tensor. All right. Okay. Let me look at chat here. I don't do this. Okay. I don't do like machine-based proof or something like that. I mean, I'm just not very interested. Okay. So, um, okay. And I have too much stuff um, to do anyway. So I'm sorry if I won't be featuring any of those things. Okay. All right. So here we have these assumptions, and from this assumption, you can actually show higher order quantities, higher order moments vanishes. You can actually show that, and let's actually see an example of this. Okay. And this is not a general proof, but hopefully we can get the idea across. So from these assumptions, you can actually show the higher order moment vanishes. Okay. So this is our claim. Higher order moments um, um, in analogous form to 2 and 3 vanish. So you don't need to make further assumptions about higher moment. So that's what we're trying to get to. So for example, let's consider the following. Okay, let's consider a third moment. Say the integral over x minus z absolute value less than epsilon dx times dxi minus zi times xj minus zj times xk minus zk, and then times the transitional probability density, p of x at t plus delta t given zt. Okay, let's just write it as, say, let's define this to be, Cijk. Okay, this is a Cijk which depend on z and t times delta t, and then plus the order O epsilon. Suppose you have this. We want to show that c is identically 0. Okay, so yeah, so this is what we want to show. We can show Cijk is identically 0, or it should be more say accurate. It should be O epsilon. Okay, we can just by assuming 2, 3 vanish, assuming you have 1, 2, 3. Okay, so that's our assumption. By our assumption, you do not need to make higher order moments anymore, right? You do not need to make assumptions about higher order moments anymore. They are automatically vanishing. So how do we do that? So here's a quick observation. This is symmetric. This Cijk is symmetric because if you change the order of the factors xi minus zi, xj minus zj, xk minus zk, if you change the order, of course, the integral doesn't change. So this is symmetric. So you can think of this as the coefficient of a trilinear form. You think of a trilinear form. This is natural because B is related to covariance, right? Because covariance is a bilinear form. So you can easily think of Cij as representing some trilinear form. And here's the proof. So notice that Cijk is symmetric. in the indices. Oh, hi. Hi from Prague. I didn't know you're, I have viewers from Central Europe. Okay. Hi from Canada. So Cijk is symmetric in indices. So for that, we can consider this trilinear form, the sum over ijk, alpha I, alpha j, and alpha k, Cijk, zt of z and t, okay? And let's just call that, define this to be c bar, okay? Define this to be c bar of argument alpha. Alpha is a vector, zt. Consider this. So this way, this is a trilinear form. This is a trilinear form so that Cijk can be expressed as a derivative of this thing. So just like in a linear form can be written as the first order derivative of a vector can be written as a derivative, partial derivative, or a gradient of a linear form. Right? If a matrix can be written as the Hessian matrix of a quadratic form. The Hessian matrix would involve second order partial derivative, and now you need third order partial derivative, which is 1 over 3 factorial d cubed. Or you can think of this in terms of Taylor expansion. Both are equally valid. D alpha I, D alpha j, D alpha k of C bar. Alpha zt. Okay, so that's the expression, and now we can show that C bar is of O epsilon. We show C bar equals O epsilon. Because C bar equals O epsilon, so therefore the coefficients Cij is all O epsilon. So C bar equals O epsilon. So let's show that. Okay. So let's consider a bound for C bar. Let's consider a bound for C bar. So C bar modulus. Okay, how can we express C bar as a how can we express that? So you can in the definition for Cij, if you divide by delta t on both sides, Cij becomes a limit. Cij becomes a limit of this integral divided by delta t as delta t tends to 0. So you can do the same here. You can write this as the limit of delta t tends to 0, 1 over delta t, the integral x minus z modulus less than epsilon of here. You wanted to how can we express the trilinear form in a vector format? Notice that we just need an upper bound. So you can write here, let me think. So here you alpha I, alpha j, alpha k. You can write alpha dot with the vector xi here because of xi minus xj, so that's vector x minus x vector z dot product taking absolute value. cubed. Taking dot product cube. And then you would have what? Then you would have the hang on a second. And then times the density, yeah, x p of xt plus delta t given zt at dx. And then plus o epsilon. It's just from the definition of C. Okay, from this definition of C, you have this upper bound. And now you apply Cauchy-Schwarz inequality. Just use Cauchy-Schwarz inequality for one of the factors here. So this is less than or equal to, use Cauchy-Schwarz inequality, let's write that on the side. X times y dot vector, dot product. The dot product absolute value is less than or equal to x modulus times y modulus, or length, whatever you want to call it. Okay, so I've been doing like complex variables and vector stuff, so I kind of tend to mix up the name, norm, absolute value, modulus all the time. So hopefully this does not cause any confusion. So here you see alpha is a constant vector, so you can be taken out of the integral and the limit. So you have alpha norm up here. Alpha norm up here, and x minus z. X minus z, well, x minus z can be taken out of the integral, but x minus z modulus is less than epsilon, so you can write an epsilon for the bound for epsilon. Okay, so here you have, I'm saying is alpha dot x minus z absolute value, this is less than or equal to alpha modulus times x minus z modulus. X minus z modulus is less than epsilon because of the integral. Okay, so and now you have what's that? And now you're left with a now you're left with the integral 1 over delta t, the integral x minus z absolute value less than epsilon, alpha dot with x minus z, alpha dot with x minus z quantity squared, or absolute value squared, x p of x, the probability density function, dx, and then plus o epsilon. And this would be, okay, here, this would be equal to epsilon. Oh, I forgot the limit here. Sorry, I forgot the limit here. Limit delta t tends to 0. Okay, so yeah, this is epsilon times alpha norm times alpha I alpha j, and then bij. Bij. There should be a summation here. There should be a summation over ij because of all the dot product and stuff. Okay, and then plus o epsilon, finally plus o epsilon. But as you can see, this is a constant. So here you have epsilon, and together this is just o epsilon. And we're done. And we're done. So this little proof tells us that our assumption here, namely, we made assumptions about finite jump, that is a non-local transition, as well as local drift and local diffusion. From these assumptions, you do not need to make further assumptions about higher moments anymore. And we use the third moment as an illustration. And you can similarly show all the corresponding higher order quantities vanish. Okay, so there you go. So it's you can intuitively think of the first assumption, that is W. This is associated with discontinuous motion, like in the Poisson process. So W is about discontinuous motion. Where is that? Yeah, like a Poisson process. And A and B are about continuous motion, where A is about continuous deterministic motion, and B is about local random motion. Okay, so hopefully we have stated our assumption quite clearly. Okay, let me go back to chat. Is everyone lost? Oh, no worries. Okay, I sorry if I came off as dismissing language or code. It's just the priority of the channel. No, doing code, I mean like, for example, you know, like doing some live coding for stochastic simulation or numerical methods. I don't think I will be doing much of those things on the channel. Sorry, Nadia. Okay, I did not mean to dismiss those aspects. Okay, Lean is, as far as I know, a machine-proof language, which is even further from what I do. Okay, so because I have very little background in mathematical logic and those kind of thing. So no. So I saw you heard you were doing coding and wonder what kind. Okay, I mean in real life I do code, but on the channel I want to focus the content on mathematical foundation as a whole. So even when we do things like technology heavy fields like statistics, and in the future also numerical analysis, foundations of machine learning, I wanted to focus purely on the mathematical foundation. So you can think of the channel as kind of like applied math in subject matter, but pure math in terms of pedagogy and presentation. It's going to be very minimalistic, just a notepad, okay, just a notepad, and perhaps every now and then some other resources like published notes and whatever. Okay, sorry, Nadia. Okay, hopefully it's a few. Okay, so these are some discussion about geography. I follow this part. Okay, great. Okay, great. Okay, awesome. So I was worried that whether this sounds too abstract because we didn't have a lot of time to do examples. We only introduced one concrete example in detail. That's the Brownian motion. But the thing is, in the book by Gardner, so I'm largely following the book by Gardner. That's this book. I'll show you the book. Gardner, Stochastic Methods. Because Gardner's book is rather succinct, these assumptions I just listed were just stated as mathematical expressions without explaining much of the context. You really have to unpack them. So this one here, this is the book I've been following. I didn't follow Professor Scott's notes because I felt like Gardner's treatment is more general. So for good reason, right? After all, this is a book. That's the Professor Scott is a note. Is for like if you find the book too overwhelming, you can go check out the notes. So as a manual of sort. So right now we are following chapter 3, Markov process. Do we have a list of content here? My goodness, there's not even a list of content. Okay. So I'm just going to do a screenshot, okay? Do a screenshot of which exact section or chapter that we're doing right now. Okay. Hang on, guys. And guys, let me try to find the text. I'll give you the list of content. But this is an old list of content. I don't have the digital copy of the latest edition. I do have a physical copy. I do have a physical copy on my desk. Like right now, I'm reading it. So this is what we're doing. We're doing chapter 3 in Gardner's book called Markov Process, and in particular section 3.4. Here, this is a screenshot. We're doing this one. Differential CK equation. Okay, so we now have about 2 hours and 20 minutes left, and hopefully in that period we can finish the derivation. Because the derivation is, mathematically speaking, is not challenging. In fact, it is elementary. It's just basic calculus, okay? But because of the cumbersome expression, it takes some time to disentangle the mess, all right? Okay, so hopefully we're clear on that. We're doing this part of Gardner. This is from Gardner Handbook, Gardner's Handbook. And it's quite readable if you come from a physics background. The language, the notations should be familiar. All right? Okay, so let's continue. So what do we want now, right? We want to derive the differential Chapman-Kolmogorov equation. So let's consider the derivation. Let's now dive into the actual derivation. Okay. We're going to consider a so-called test function. A so-called test function f of x. This is an arbitrary function with no physical meaning. X is a vector. A test function. F is scalar valued. Okay. This is a test function which is twice differentiable. Okay, so here, where's chat, guys? Where's chat? Numerics, I'm more aware my background is too. Okay, great. Okay, great. We will do some numerical analysis, like numerical linear algebra, root finding, perhaps numerical PD. I think numerical PD is unskippable at this point because if you're discussing PDEs for a practical crowd, you cannot avoid numerical PDO. Perhaps we'll start with finite difference methods. I think it will be a great companion to our discussion of heat equation. Okay. Anyway, so consider this function, and we're going to now once again consider operation. So at this point, at first it might sound a little bit unmotivated, but I'll explain why we consider a test function. Okay, so we want to consider the expression d over dt of the integral here. The integral region is unspecified yet. Okay, so just the integral and then dx. We'll do the integral region later on. Dx and f of x times the transition density function p of xt given y and t prime. So that's what we're trying to express. So eventually we want to pass on the time derivative inside. Eventually this is what we want to do. So this way we can get a time evolution for the transition density. Okay. The reason why we multiply f of x will become clear later. Essentially, we want to do an integration by part. That's the main motivation, and we'll see how that is accomplished. So we can first write down the expression using the definition of partial derivative. This is the limit of delta t tends to 0, the integral dx, okay, f of x. Let's just write 1 over delta t up front. Okay, the change in the integral the change in the integral, so it will be the integral dx f of x p of tx and t plus delta t given y t prime. And then do the integral over dx f of x p of x t given y and t prime. So that's the change in the integral. Okay, and of course you can combine them into a single integral. Integral dx f of x, and then p of, use curly bracket outside. Actually, we don't need the bracket here, just a single integral. The integral dx fx p of x and t plus delta t given y t prime minus p of xt y t prime. Okay, so now we have 3 time instances. Notice from the equation we have 3 time instances. Let's draw the diagram here. T prime, that's the earliest time, and then you have t and also t plus delta t. Okay, let's use the CK equation to express this quantity here. Classic diagram for CK equation, integrating over the intermediate state, which is this state at t. So let's call the state at t to be z. Okay, so the initial state is y. Right, the initial state is y, and the final state is x. No? Here, the final state here is this is x. This is x. So we're looking at this quantity here. I want to use CK. The final state is x, and let's call the intermediate state z. Okay, so let's write it down. The limit of delta t tends to 0, 1 over delta t, integral dx f of x. And here you have another integral. This is the integral over the intermediate state called dz of p of x t plus delta t, intermediate state z at time t times the density of p of z at time t given y at t prime, right? Initial state y at time t prime. Okay, so that's the CK equation now successfully applied, and the remaining is unchanged. Okay, so that's the CK equation. So now what do we do? So we're going to consider the integration region. Integral over x into 2 regions. So here, now the key idea is, you want to split the integral. Split integral over x into 2 regions. Here, this is the diagram here. You have the point z. This is the initial position. And here, this is a ball with radius epsilon, like we draw it in our assumption part. Here, this is a ball with radius epsilon, RD. We're integrating x is in RD. Okay? X is in RD. Z is considered fixed. The initial condition. Into 2 regions which are x minus z length greater or equal to epsilon, and x minus z length less than epsilon. Okay. So when x is inside the ball, when x minus z modulus less than epsilon, you can do a Taylor expansion. So here we're doing Taylor expansion for f. Taylor expansion for f would look like this. This is a multivariable Taylor expansion, so notation is going to be a little bit cumbersome. F of z is the base of expansion, the center of the circle, plus the first order terms, which is the sum over I, df of z over dx dzi times xi minus zi. There's that. That's the first order term. And then you have the second order term, which is half the sum over ij, multivariable Taylor expansion, d square f of z over dzi dzj, okay, and then times second order power xi minus zi times xj minus zj. And finally, you have the remainder term, and the remainder term has the form, okay, assuming a second order differentiable, twice differentiable, okay, so you have the remainder term of the form x minus z vector distance squared, okay, this is the distance between x and z squared times the coefficient rxz, okay, where rxz tends to 0 as x minus z distance, x minus z length tends to 0. The distance between x and z tends to 0. Okay. So basically, what it says is the remainder term is the distance, of between x and y, between x and z squared times the coefficient that tends to 0 faster than that. This way, it ensures that the remainder is a higher order term compared to the second order term. Okay, so that's just some basic calculus, right? It's some basic multivariable calculus, Taylor expansion, definition of differentiability, and whatnot. Okay, so that's the key idea. Okay, so that's the key idea, and what we want to do is we want to substitute this f into the integral. Why on earth would we want to do that? Well, you see, in the Taylor expansion, we have partial derivatives for f. So by an integration by part, we can transfer the differential operators onto p. This way, you get a PDE. Hopefully, we get a PDE for p. Okay, so that's the idea. So now substitute f and then integration by part. That's the overall strategy here. Of course, writing this will be a little bit complicated. Okay, so just have a little bit of a patience and we can grind through it. Okay, and that's the derivation for what's called the master equation, and Fokker-Planck-Kolmogorov equation. Okay. All right. Okay, hang on. Now let's do the substitution. To substitute the Taylor expansion into star. In a star. All right. So here, the integral with respect to dx has two terms essentially, f of x times this integral from ck equation and the last term. So how should we set this up? How should we set this up? Well, here f of x, right? F of x has four terms. See, in the Taylor expansion, f of x has four terms. The constant term f of z, you have the constant term f of z, and these two terms involve the first and second order derivatives. Okay, and the remainder term. Okay, let's consider things separately. Okay, so the most difficult part is, of course, the integral from ck. And as we mentioned, we want to split the integration region into inside the ball and outside the ball. Yeah. So let's do the integral inside the ball first for the first integral. Okay, so for the second integral, we're actually not going to split the integral. Okay, so let me emphasize that. So here, split the first integral. Yeah, so actually, let me add an extra step, okay, just to make things a bit cleaner. So I'm gonna do an extra step here. Perhaps I shouldn't split this, huh? I shouldn't split this anyway. So, okay. So I'm gonna change things a little bit. Right at this step, right at the second step, I'm gonna use ck. Okay. So here, sorry guys, this is ck, and I'm gonna delete the middle step because it's kind of pointless, right? This is not very useful. This is not very useful, so I'm going to delete this step just to make things a bit clear. Use ck here. Put the diagram up there, and here you have the limit. Okay, so this is the first integral. This is the first integral. Okay, the second integral, we're not going to mess with that. Here, the second integral is unchanged. It's still this term up here. Once again, nothing substantial, just you can even think of it as a typographical change. Bracket here. So here, the key idea is to split the first integral over x into two regions. First integral. This one. Into two regions, and then do Taylor expansion and then substitution. Hopefully this is more manageable. Okay. Okay, so you get this massive expression. So in the first integral, you have say here. I'm going to write it this way. We split the integral to two, and inside the sphere we have four terms. And the outside of the sphere, because Taylor expansion don't apply, so there's just one term. All right, okay, let's try to write that. I'm running out of space here. Okay, I want to keep this expression here and the Taylor expansion on the same page, but perhaps it's a little bit difficult to do that. Okay, this is actually where we got lost last time. And now we're going to fix it. It's just difficult to write down, okay, but let's do it. So here you have let's write it as a double integral. Here, just the integral, without the limit and the delta t, just the integral. Focus on this integral. The integral, here you have two integration variables, dx and dz, and x minus z absolute value less than epsilon. Okay? And inside that integral, plus what's outside the integral. Greater or equal to epsilon. And as I said, outside the integral, we're not going to actually do anything about f. So this is just f of z, f of x actually, f of x. Okay, this is f of x, and then times what's after. So this is unchanged. Integrand in the CK equation. So this is what's outside. That's unchanged. And inside, you're still integrating the same function, but now f of x needs to be written in terms of the Taylor expansion. Okay, so let me just based on that and change a few things. Okay, so here, this is outside of the sphere, the ball. Okay, and then in the Taylor expansion, what do you have? Let's write three terms. Okay, you have the constant term. This is f of z, the zeroth order term in the Taylor expansion, f of z, multiplied by this thing, the same product of densities here. Okay, and then you have also the integral inside the region, times the first order and second order term. So let's combine them together. Okay, this first and second order term in the Taylor expansion, this thing. Here, times the product of density. It just needs a little bit of a patience to grind this through. I'm even running out of horizontal space. Let's put a multiply here. Okay, multiply. This is the next term. And you also have the remainder term. Like Christian called it yesterday, it is dirty work. Yeah, it is kind of dirty. Okay, so and then plus the same integral, the same integration region, okay, integral dx dz over the same region inside the sphere. Let's put it here, and then you have the remainder term. This is the remainder term. The remainder term times the product of density again. That's the remainder term and times the product of density. I'm copying, pasting a lot to save some writing. Okay, so that's the first integral. And because you have all of this as a double integral, so we want to write the last one as a double integral as well, so that we can combine stuff. That's the idea. So how can we do that? Well, we want to make all the density a product. You see, here you have a product of density. Here you have just a single density. So let's create a product. And to do so let's imagine. Okay, let's imagine if you have say, hang on, how can we change that? We can change the integration variable to be z, just changing the dummy variable for the last term. For the last term, let's change the dummy integral to z so that you can have the same integral z to make them the same. Okay, you want to here. Let's change to dz. So this one, dang it. Change to dz. Okay, so you have a p of zt given y and t prime again. Okay, and this now is integral of dz, but to create a product, you want something like this. So you want to have, hang on a second, I want to do this. Okay, I want to write it this way. Okay, so you want an integral over here. Change that to dz. You can integral of dz f of z, right? F of z and p of zt given y and t prime. And now you wanted to create a product. To create a product, you can do something like this. You can multiply that by 1. Multiply that by 1. What do we mean? Use a normalization condition of density. So this is integral of dx. Integral of dx, and here the p of x and t plus delta t given zt. You see, because you're integrating the future state over possible future state dx, this is just 1. This is just 1. Okay, so here you can write the integral of, yeah, this is what it turns out. This part is now here. And you can write this as a double integral dx dz f of z, and then the product of density again, p of x t plus delta t given zt, p of z t y t prime. Okay, so yeah, this way you transform the second one. You've written the second one as a double integral, so that you can combine with the earlier terms. All right, so here I'm gonna move this term downstairs to minus this integral. Minus this thing here. So that's the whole integral. And then, of course, you need to divide that by delta t and tend to let limit delta t tends to 0. So this is star. Yeah, this is star. Star equals this. Okay, it's ugly, but hopefully we can simplify this, and we can. So now we're going to consider things line by line. Okay, hopefully everyone is still not completely lost. Okay, so let me reiterate. Okay, so let me reiterate here. So here in the star, you have two integrals. We want to split the first integral over dx into two regions, inside the sphere, outside the sphere. The sphere is of radius epsilon, centered at z. And over that sphere, we do a Taylor expansion of the test function f in the hope of passing the differential operator acting on f to p. This way you get a differential equation. That's the hope anyway. Okay, so and for the second integral, we arbitrarily we try to make it look like the first one, so that you want a double integral and you have a product of density. That's not super difficult to do. You just change a dummy index and you multiply it by a normalization condition. And inside the first integral, as we said, you have two regions. Outside the region, we don't use the Taylor expansion, so that's one term. So this is outside the region where no Taylor expansion is used. And inside the circle, inside the sphere, the ball, whatever you want to call it, we have three terms. We have three terms. The zeroth order term, the first and second order term together as one integral, and lastly the remainder term. Okay, so hopefully this is all sorted out, even though it looks horrendous. Okay, so let's label these. Okay, let's label these as line 1. Let's call this is line 1. Looks like base model. I'm not quite sure what that is. Perhaps that's something in physics. I'm not a physicist, so I'm not quite sure. So this is line 1. We say something like this. This is line 1. Line 2. Line 3. Line 4. Line 5. And this is finally line 6. All right. Let's first try to let's consider line 2 and 3, because this obviously has something to do with our assumption. This obviously has something to do with our assumption regarding the jump moment. So line 2 and 3, what happened? You can interchange because of the uniform assumption. Right? In analysis, uniform assumption allows you to interchange integration and limit. The integration, interchange the integration and limit, okay, allows you to write. Okay, this is just the first moment. Here you have the first moment condition in our assumption. Here, in the first order assumption, the first order moment is about drift. Right? Remember here, assumption 2. This is about drift. So, putting the limit inside the integral, limit 1 over delta t inside the integral, you get assumptions 2 and 3. So therefore, let's write by assumption 2 and 3, line 2 and 3 becomes the following, becomes the integral over dz, because the integral over dx is already included in assumption 2 and 3. Okay, so that was like an hour ago, so in case that looks unfamiliar, assumption 2 is about local integration, so the local drift coefficient, integral over dx. Integral over dx, and then p of x t plus delta t, z z and t. Okay, so that's A. So here coming to the integral, what do you have? You have in the Taylor expansion, this is the first order displacement term. This one, dx gives you AI. Okay, so that's it. So here you have integral over dz, and the summation is still needed. The sum over I is needed, and then you get AI of z and t. Let's just write AI, okay? AI, just the notation is already very cumbersome. Sum over AI, and then you have df over dz, df over dzi. Once again, evaluated at z. And you kind of have the same situation for the, for what? For the, here. For the second moment as well. So you have, this is the sum, ij, half, okay, half sum ij, bij, and then d square f over dzi dzj. I know, right? Okay, cool. And then what else? The integration only involves one transitional density, so the last one remains. So you get p of zt given yt prime. And then plus higher order terms, not higher order terms, but O epsilon, right? Same order, O epsilon. There's that. So this is our assumption 2, 3 comes into play. Okay. Where do assumption 1 come into play, huh? Well, assumption 1 is about quote-unquote zeros order moment, right? Assumption 1 earlier is just the rate of change for the density itself. And it actually, we're also considering finite jump. So that's outside of the, here, assumption 1 here. We're considering outside of the ball. Assumption 1, that's the jump rate. And has nothing to do with moment. So it probably has something to do with the last two integrals. These two integrals should have something to do with w. Okay, so we should substitute that in there. Okay. Anyway, so this is a line. Hang on. Four to six together. Actually, you know what? No, not 4 to 6. Line 1. We want 1 here. Hang on. Outside, yeah, we want outside here. We want outside. Let me see. 1, 2, 3, 4, 5, 6. So we want the terms that don't have any moment. So that's line 1. Yeah, that's line 1, line 5, and line 6. Those don't have moment. They don't have moment up here. Okay, and they get combined into the integral about the rate of change of the density itself. So let's do that. Okay, so 1, 4, 5. 1, 5, 6. Take a closer look at these. 1, 5, and 6. And we're going to use assumption 1. That's the rate of change of to replace these. Use assumption 1. So this will be W, right? These are all be W of x given zt times delta t. And then you take the limit, delta t cancels, so you're just left with W. So what do you have left? You have f of z. You have f of z and the hang on a second. You have f of w. This is w. But see, this is x. This is z. They aren't the same. They aren't the same. So to factor out f of z, you need to do another change of index. Yeah, so for the last term, you see z and x are all dummy variables, so they can be exchanged. Because you see this is f of z, this is f of x, this is f of z. They need to be changed. They need to be changed. First, let's take a look at line 1 and line 5. Okay, so let's figure out how this works. Line 1 and line 5 combined together. So the distinction between the two integrals, actually, you know what? No, this is not good. This is not good. This is not good because only outside the region you can apply this assumption. That's why I wrote it here. So perhaps there's a cancellation going on. Yeah, there's a cancellation going on, isn't it? Because here the integral inside the ball is a plus sign, and this integral outside the ball is a minus sign. Okay, so actually, you know what, guys? I'm going to do it on a separate page because it's kind of difficult to think purely in your mind. I'm not Feynman. So here, I need this line. I need line 1 for sure. This one does not involve moment. Okay, I need line 1. I need line, actually just copy the whole damn thing. My goodness, this is okay. So I'm going to copy the whole damn thing, and I'm going to keep what is relevant to assumption 1. Okay, we already took care of line 2 and 3. So that's, you can consider that's what, 1/3 of the work done. Okay, so now, okay, what I want. What the heck do I want? I want the limit of 1 over delta. Line 1 I need. Line 2, line 3 is taken care of, so they can go away now. Okay, and I don't want it to look at the remainder. I don't want to care about the remainder. It will be handled later. So these are the lines. Line 1, line 2, line 1, line 5, line 6 together. Okay, this equals what? This equals the limit of delta t tends to 0. So 1 and 6 together, 1 and 6 together leaves out the integral for outside of the sphere, outside the ball. So here you have the integral. Line 5 gets unchanged. X minus z quantity x minus z modulus greater or equal to epsilon dx dz. Now line 5 remains f of x, so I'm just going to copy things. Okay, I hate writing this. There you go. Line 5 and line 6 have the same integrand. Just want to make sure. They have the same integrand. F of z, p is the same. We constructed this way. So, therefore, line 1 and line 5, line 1 and line 6 can be combined. So let's write it as minus integral x minus z greater or equal to epsilon dx dz f of z. See, f of z. So this is the difference here, f of x and f of z. And now you want to factor out f of x. So to do so, we would interchange x and z, because x and z are dummy variables, so you can do that like this. Okay, so here in this is a new expression. Okay, once again, we're not going to do anything about the first line yet. We want to interchange the integral. Interchange not the integral, but the variables, dummy variables, in the second integral. The second integral is by combining line 1 and 6. I'll just put an arrow here. This is by combining line 1 and 6. Okay. Now we're going to interchange the variables. So x becomes z, z becomes x. Okay. So here, from the right, z is here, so we put an x here. Z is here, you put an x here. X is here, you put a z here. Z is here, you put an x here. And dz becomes dx, dx becomes dz. So that now you can combine the two integrals and factor f of x. So this would be the limit delta t tend to 0, just one integral. Oh, did I miss a 1 over delta t? Yeah, I did. 1 over delta t. 1 over delta t. Here, the integral x minus z modulus greater or equal to epsilon dx dz. And f of x times here, the product. It looks like the product of density, but with order reversed. Okay, we didn't wave hand. There you go. Minus sign here. And then we can use assumption 1. By assumption 1, you can write this in terms of w. So this way you get limit delta t tend to 0, 1 over delta t double integral x minus z greater or equal to epsilon, and now you have this is dx dz, f of actually, what do I want? I want to have okay, this is f of x, right? This is f of x, and here you have the assumption 1, right? Let's put assumption 1 on the side so it becomes easier to follow. This is assumption 1, the W function. Oof. This is W function. Do the substitution here. Okay, now you have W here, W of x given z, right? This is the first one, W given z and t times delta t times p of z t given y t prime minus, here this is W of z, right? Z and W got switched up. Zx t delta t, here delta t, and then times what? Times p of x is x and t y t prime. That's it. Right, plus higher order term O delta t. Okay, but then again, if you take the integral, you take the limit, then this delta t goes away. So it's just the integral, the integral of x minus z modulus greater or equal to epsilon. So this is assumption 1. Okay, here we use assumption 1, dx dz, f of x, and then quantity w, x given z t, p of x, p of zt given yt prime minus w z x t p of x t given yt prime. Okay, so this is 1 now. So this is the 3 lines, as we said earlier, line 1, 5, and 6. Oof. So eventually we also want to let epsilon tend to 0. Eventually we want to do that. We still haven't taken that limit yet, right? But this is so far, right? We only use the delta t tend to 0. Eventually we'll let epsilon tend to 0. So I think this is okay for now. Yeah, use assumption 1. We used assumption 1, so this should be all right. Yeah, let me just double check. F of z, w of x, yeah. Okay, that's fine. That's fine now. And so what do we have remaining? Is there anything else? Yes, there is one more thing. That's the remainder. That's line 4. So for line 4, you have a remainder. And for that, we can use the remainder estimate to show this tends to 0. Okay? So here, what do we want? We want 1 over t times line 4. We want that. So how can we argue that? Well, the remainder has an estimate. The remainder is uniformly bounded, no? It is uniformly bounded. So the you can say the remainder, which is this thing, x minus z modulus squared, x minus z modulus squared times r. R is bounded. You can use the bound for r. That should be okay. All right, that should be okay. And then you integrate it, integrate here, this one, the second, this is like a second moment term, right? If you bound r by a constant, what remains inside the integral is the second moment. The second moment, which is the function b, right? Which is the function b, and then times the modulus, right? The modulus of r, or just the absolute value of r should suffice. So basically, due to the fact that r tends to 0 as z tends to 0, as z tends to 0, line 4 is bounded by the second moment times the maximum of r. It looks like the second moment times r, so that tends to 0. Let me write it down. So line 4 tends to 0. We need this integral divided by delta t. This is line 4. Line 4, 1 over delta t of this thing. Let's take the absolute value. So first of all, let's take out the maximum, or the sup. Let's use sup, because this is a open set. You might not have a maximum. The sup of the r term, that gets taken out of the integral. And here you got 1 over delta t. Here, 1 over delta t. Because this is less than or equal to, we can say this is less than or equal to, say the integral, let the z to be to take range over the entire RD. Right. So if d is taken over the entire RD, z is taken over the entire RD, then this part you can ignore that. So can we say that? Not ignore, but by normalization, this part is 1. This part is 1. So you just say you have integral with respect to x minus z modulus less than epsilon, and x minus z modulus square times p of the transition density. Okay. There you go, taking the absolute value. As delta t tends to 0, this would be the second moment, the diagonal terms, because it's modular square, so you don't need all the terms. You see, this is the length. Length only is the sum of squares, so this is just bii zt over I, single sum, not double sum, plus O epsilon times the sup of the r function. X minus z less than epsilon. And this is O. This is O epsilon, little o epsilon. So eventually you want to let epsilon tend to 0 as well. Okay, so here we already let delta t tend to 0, and eventually you want to let epsilon tend to 0 as well. So what happens when you take epsilon tend to 0? Well, for this part, you just ignore the O epsilon term, and this part needs a little bit of a thought here. The jump term needs a little bit of a thought. We need to sort out the notations. And the last one, well, the remainder term goes away. The remainder term goes away. So combine all of these, you finally get the equation, right? So basically, we're almost there. Okay, we haven't done the integration by part yet, but basically now we have the following. Okay, so therefore, now you have the following. So far, after letting epsilon to 0, we get the following. So by the way, what is this originally about? What is this originally about? Well, the original left-hand side is this thing. So here, let's put that as the left-hand side. This is the left-hand side, and let's pick up the survivors here. You got, here's the survivor, this one, without the O epsilon. Okay. There you go. So there's one term. We want to do integration by part. We want to do integration by part so that the partial derivative gets passed on to p. That's the original idea. Okay, and we also have this term here. So we want to say something about this when epsilon tend to 0. So when epsilon tend to 0, okay, we write it as the following. We write this one as the following. So as epsilon tend to 0, this is the integral over hang on. Here I have a dx here. You can say integral over dx f of x, yeah, and let's introduce a notation. Call it integral bar. Yeah, let's call it integral bar, and then dz of what's inside, dx, right? dz of this thing. Okay, so what does integral bar mean? Well, it just means the integral of outside the sphere as limit tend to infinite, limit of epsilon tends to 0. Okay, so we introduce this notation, limit of epsilon tend to 0, the integral over x minus z modulus greater or equal to epsilon. This is defined as this notation. Okay, this is defined as this notation. So basically, any strictly positive jump is included as contributions to this integral. Okay, so that's what we have here. All right, it should looks good. It looks good. Okay, so here we have, this is another survivor after taking epsilon 10 to 0. That's another term here. That's another term here. Okay, so so what do we want, right? We want to pass on the partial derivative to p, right? That's what we want. Okay, so you put a plus sign. This is a plus sign. This is a plus sign. So how can we do integration by part? Well, integration by part involves two things. You pass on the differential operator and will generate quote unquote a surface term. Right? Just like in the regular integration by part. What's the vector version of integration by part, guys? The vector integration by part, this is a multivariable function. The vector integration by part, I need to look up the formula. Hang on. Multiple integral integration by parts. Do we have that? This is well known, right? Single integral. You see, you pass on the differential operator to the other function. This is what we want, but at the same time, we'll generate the quote-unquote surface term, endpoint terms. But that's the 1D situation, right? So you have just two endpoints at the boundary, or quote-unquote the surface of the region. For multivariable stuff, you need a surface integral. Multivariable version, do we have that here? Perhaps you should use divergence theorem to derive that. Is that right? Where's the multivariable integration by part? Higher dimension, yeah. Yeah, so by the product rule of divergence, higher dimension, multivariable version requires the product rule to divergence, because integration by part really comes from the product rule for differentiation. Okay, so now integral on both sides, because this is a divergence. Divergence taking a volume integral gives you a surface integral. Yeah, so after integration, left-hand side is an integral over the boundary. So that's a surface term. And the two terms on the right-hand side are the, what's that? The two terms on the right-hand side. You see, this is the divergence. The divergence of V. Divergence of V times U plus the gradient of U dot with V. So rearranging gives us this form. Rearranging gives us this form. Okay, so let's write this formula down. Okay, so let's write this formula down. So let's recall multivariable, multi-integral, multiple integral integration by part. Recall. Multiple integral integration by part, by parts, okay, which really is based on divergence. Okay, so you have the integral over omega u times nabla dot v. U is a scalar, v is a vector, and then d omega. So that's a volume integral equals the integral over gamma, which is the boundary of omega, gamma, which equals d omega, and then uv, that's a new vector field, the scalar u times the vector v, dot with n hat, the outward normal vector. Let's draw the picture here. Okay, so this is omega. boundary is d omega is gamma, and look at the surface element. This is outward vector n hat. Okay, so that's the diagram minus the integral over omega gradient of u dot with v and then d omega. So this is multiple integral integration by parts formula. So we want to do something about this first term here to do the integration by part. Right? So as you can see, it will generate a surface term. It will generate a surface term. So what we have not yet actually specified the range of integral. Okay, so let's now define the surface. Let's now define the surface. So let's say your the integral is over a region R with surface S. So let the integral be over a region R with surface S. With surface S. Then what we have? Then we have the first integral here. Let's call this double star. Double star integration by parts will become the following. So you have the integral dz. You see, this is the sum of ai, times this thing, So here the sum of ai, this will be the, what's that? Does it look like a divergence? This looks like a dot product, actually. Maybe I should change it here. Maybe I should write, yeah, I should put here and here. Yeah, sum of ai times the partial derivative df zi, that's the gradient of f dot product with a, with the vector a. Okay, so on the right hand side, the moral is you have a negative sign due to integration by part. You get a minus sign. Minus sign dz. U here, what is u? U is f. U is f. So you have f of z times the divergence of the vector. Times the divergence of vector. What's the vector? The vector is ai times the density. So there you go. You get the sum over I, d over dz I acting on ai times p. ai times p. So yeah, ai should depend on z, t, and p is a function of z, t, y, and t prime. There you go. Okay, so you have this term, and you also have the second derivative term. So second derivative also needs integration by part, but in that case, in the second derivative, I have not written the surface term yet. Okay, so let's put the surface term. But I'm talking about the second order derivative. To do integration by part by second derivative, you pick up a minus sign twice, so that's a positive. So integral over z, integral, so this is the integral over the region R. Okay, I can finally write region R here. And then integral of dz fz times half the sum times the half of, so once again, f is freed from the differentiation yoke. And now you can act the second partial derivative operator, d squared over dzi dzj to bij of zt times p of zt given yt prime. Okay, so that's it. That's it. Okay, so that's basically the problem. Okay, so that's the second order integration by part, once again plus surface term. So that's double star integration by part. Okay. And now we need to argue that the surface term vanishes. So that's the other thing. I will just use Gardner's argument because I'm sick of writing this. Okay, so here I'm going to use Gardner's own comment here to justify why you can ignore the surface term. Why ignore surface term? Okay, here's what he has to say. We have not, okay, so here you have specified the integral range, R and S. Okay, it says, he says, then clearly, the transition density, P of x and t given z and t prime is 0. This is 0 unless both x and z is in R. Okay, so what does that mean? So here, let's draw a diagram here. Okay, for simplicity, I'm just going to draw a 2D diagram. Okay, so this is to represent RD. This is Z. Okay, let's imagine this is R. Okay, not necessarily a ball, arbitrary. Okay, why do I draw this shape? Okay, just say arbitrary region. This is Z. This is R. This is R with boundary S. dr equals S. So it says this is 0 unless both x and unless both of them are in R. Hang on. If x is not in R, I think that's a typo, huh? In the second line, W is 0 unless both of them are in R. X and Y are in Y. What's Y? Because this should be Z. This should be Z. What does this say? It says unless the initial and final state are in the same region, the transition probability should be 0. Chad, what do you think? Does that make sense? And the jump rate is the same. It's 0 unless both x, I suppose this is a z. This should be a typo. But the conditions on AI and Bij can result in discontinuities in these functions defined by what's 3.42. 3.42 is, I believe that's the condition. Yeah, 3.42 is the condition. Yeah, that's the assumptions. The assumptions about, or the definitions of the drift and the diffusion tensor. It says, but the conditions on AI and Bij can result in discontinuity in these functions defined by yeah, so that since this function, the conditional probability can very reasonably change discontinuously as z crosses a boundary, reflecting the fact that no transition are allowed outside R to inside R. In integrating by parts, we are forced to differentiate both a, I, and bj, and by our reasoning above, one cannot assume that this is possible on the boundary of the region. Okay, let us choose f of z to be arbitrary but non-vanishing only to be, okay, let's choose f of z to be arbitrary but non-vanishing only in an arbitrary region R prime contained in R. So you want to choose a function f. Okay, so now you're doing some shenanigans with the test function. So you're this way. Okay, so by choosing f to be this way, the surface term vanishes. So f is the support of f, basically non-vanishing only in an arbitrary region R prime entirely contained in R. So basically you have this scenario. This is the support of f. The support of f is completely contained in R. Okay, so that's why earlier, yesterday I said this is a function f. F is a test function. A test function has compact support. I kind of predicted this will be used later to eliminate the surface term, basically. You choose your f to have compact support, closed and bounded support. It is perfectly smooth, but it has compact support. This way, when you choose a region that contains the region which is also bounded, okay, but contains the support of f, then you can eliminate the surface term. And this is actually quite common. I mean, just as a comment in passing, this is actually quite common in distribution theory and also in the study of Sobolev spaces in functional analysis. You want to pass on the derivative to another test function, and the test function has compact support. So f has compact support. Compact support, and is contained in R prime. Completely contained in R prime. Completely contained in R. So that's the reason you can ignore surface terms. I'm not going to pretend why I understand this part of the comment. Okay, I'm not going to pretend that I understand this part of the comment. Okay, so therefore, finally, it's time to put everything together. So on the left-hand side, you obviously want to pass the differential operator inside the integral. Okay, you want to pass it inside the integral. And what do we have on the right? What do we have on the right? Well, unfortunately, on the right, the first integral is integral over dz, not dx. Well, that's easily fixed. You just change the variable, change the dummy variable to x. That's it. Just change the dummy variable to x. Okay, and now you all have f of x times some other function dx due to the arbitrariness of f of x. Okay, we must have the relation, the final result. The final result is as follows. It says this is dt. This is dt of the transition density. dt of the transition density of p of z t given y t prime. Okay, and now you this is you get these three terms minus sum of I d over dzi of ai z ai z I z, just z, t p of z t given y t prime. Okay, and then plus half of the sum over ij bij. Oh no, second derivative. This is a diffusion term. You need the diffusion term, which is d squared over dzi dzj, okay, times bij z and t times p of z t given y or y prime, y and t prime. Okay, that's a diffusion term. And finally, plus the integral over dx w z given x and t. So after changing the dummy variables and whatnot, okay, no whatnot. I don't know why I keep saying this. Okay, bad habit. Okay, changing the dummy variables, you get this final expression, and this is called the differential CK equation, finally derived. Okay, I do not want to do this derivation again, I swear to God. Okay, so this is the full CK, differential CK equation in its full glory. And each term has its own physical interpretation. Well, why? Because we already explained the meaning of these three functions, a, b, and w. And that's actually the thumbnail. That's the thumbnail. So the time evolution of the transition density is due to three terms. First, this is diffusion. A is diffusion, remember. Oh, sorry, A is drift. What am I talking about? A is drift. A is a drift and it has a minus sign due to integration by part. This is the birthmark of integration by part. And here, B is diffusion. And finally, W is jump. All included in the same equation. Of course, in most scenarios, you only have one of these or two of these. Okay, so most commonly you would have jump process versus purely diffusion process. Sometimes you can have drift and diffusion together. Yeah, sometimes you can have that. That's actually the thumbnail. Let's check out the thumbnail, shall we? Here, I put it in the thumbnail. That's the full equation in its glory. So this is the thumbnail. We have the jump, drift, and diffusion. So what does a master equation mean? A master equation is simply including the jump. If there's only jump, that's called a master's equation. If you only have drift and diffusion together, that's Fokker-Planck. Okay, I included these four individuals on the thumbnail because Einstein was the first person who started this business. Einstein's original formulation of Brownian motion was the prototype of Fokker-Planck equation in its most general form. Okay, and Fokker-Planck, Adrian Fokker and Max Planck derive it as the generalization of Einstein's work, whereas Kolmogorov consider the most general situation. So Kolmogorov's work is more rigorous, mathematically rigorous. Okay, so we kind of bite the nail and derive the Fokker-Planck equation, Master's equation, in its most general form. For restrictive situations, for example, if you're just talking about a stochastic differential equation, you can arrive at the Fokker-Planck equation much more easily. Much more easily. But we did the most general derivation so that later on you can treat a process like stochastic differential equation as special cases. Okay, so that's the payoff here. So this is a differential CK equation, which includes Master's equations and F Fokker-Planck equation. All right, so I think I'm going to take a little bit of a break. I think I'm going to take a little break and get some water and before I come back and talk about their specializations. And we still have some time. We still have less than, yeah, it's the forward equation. Yeah, they come up in mean field differential game. I don't know much about those subjects, but certainly the Fokker-Planck equation is very significant. Is very significant. This is just this is forward. This is a forward. The other side is Hamilton, Jacobi, Bellman, which arises from optimal control theory. Okay, sure. Ask something, Mikhail. Right? That's how you pronounce the name, right? Mikhail. Yeah, go ahead and type your question. Study the philosophy of science. I'm not a philosopher of science. I'm sorry. I cannot answer this question intelligently. I would just refrain from answering it. Okay. Um, to be honest, I'm not very uh, attracted by the academic philosophy of science, or in particular philosophy of mathematics. I find them to be quite dry and not very engaging. I apologize if that's disappointment, but I personally I don't find the philosophy of mathematics to be very interesting for me personally. Okay, I'm sorry. I'm more of a practical person. This is the applied math channel, but I am interested in a more existential philosophy, but it's not philosophy of science, isn't it? I'm interested in 20th century and 19th century existentialism, Nietzsche, Dostoevsky, Kafka, uh, Albert Camus, yeah, etc. But not so much with the academic philosophy of science. Okay. Anyway, okay. I'll just grab some water. I'll be back. All right. I'm back. I'm back. So now we have the most general differential CK equation. Differential CK equation is as follows. So you have some special cases. First, let's see the master's equation. Okay, so the master's equation is excluding the jump, only keeping the jump, excluding the drift and diffusion terms. So there we go. We have the first scenario. So that is to say, there's no local motion. All transitions are non-infinitesimal. So special case is 1. The special case 1, that's the master's equation for jump process. Yeah, if you're interested in philosophy stuff, you came to the wrong channel. That's all I gotta say about it, okay? I'm not trained in that, and I don't find it interesting for the most part of the subject. I apologize if it sounds a little bit disappointing and perhaps even rude, but I'm simply not interested. So, this is just my honest opinion. Okay, you can call me ignorant, or I probably am, but well, a person's time is limited, and I choose applied mathematics and statistics. All right, so that's the master's equation. So you have AI equals 0 and Bij equals 0 everywhere. Okay, so the master's equation is as follows. So you have dt p of zt given y and t prime integral of dx, the jump rate w z given x t, p of so there are situations where jump rates are independent of time. Actually, in most applications, jump rates are independent of time. So you can just write W as a time-independent matrix. Okay. Oh, by the way, the initial condition needs to be specified. The initial condition, it's just a consistency criteria. So the initial condition simply says, if the two times are the same, then Z has to be W. Right? Then D has to be W. So no transition happens if you don't allow for any elapsed time, right? And for 0 elapsed time, the transition does not happen. So that's just a delta. Direct delta function Z minus Y. That's it. Okay. So there you go. So you have that's the differential CK equation in the special case master equation, and we will see a special example. Perhaps not today, but perhaps we'll see a very simple example called a random telegraph process. Random telegraph, which is also in Gardner. Okay, random telegraph process. If you go to the list of content here earlier, random telegraph should be an example. Yeah, random telegraph process 3.8.5. So we are now discussing 3.5. 3.8.5 is our example for the random telegraph process. Okay, and we will give SDE, the general stochastic differential equation in the Ito sense. In the Ito sense, as an example for the Fokker-Planck equation. Okay, it is easier to derive Fokker-Planck equation if you start from Ito SDE. But once again, I wanted to do it for a general macro process. Okay, so here, let's take a look at the random telegraph process. So random telegraph process also has only has two states. So it makes it very easy to describe. The transition matrix is just 2 by 2. So, and we also assume that the rate is time independent. Okay, the rate is time independent, so you get a constant matrix essentially. The W matrix is a constant matrix. So let me write it down. So the random telegraph process is binary valued. Here, they just call the two values A and B. And they don't even have to be numbers, okay? They're just two states with names A and B. X of t is in the set A and B. Okay, there you go. And here you have W, say if W from I want to say W given is time independent for all t. Okay, for all t, W from A to B. Okay, A to B is. Hang on, I want. A to B, okay, for all t to be lambda. I might need to change notations afterward, but let's just put it this way. The rate that goes from, usually write this kind of diagram here, A to B. And for continuous time process, you never have an arrow pointing towards itself. Okay, you never have an arrow pointing towards itself because in continuous time, we only specify the actual transition. Actual transition, meaning going from one state to a different state. So the rate from A to B is lambda. It's usually denoted graphically as such. So from B to A, you get another transition rate, which is mu. It's kind of like burst and death process, but you don't have actually actual numerical values for those states. Okay, and W from B to A, initial state is B, going to A, the rate is mu. Rate is mu. So in that way, the integral is now a summation. Actually, you know what? Let's write the integer valued state space as follows, or the discrete state space, the discrete version. Because the random telegraph process falls into the discrete state category. So for a discrete state, which is quite often, for discrete state space, the integral reduces to a summation. You have dt p of, because of integers, let's just use n. Okay, n t and n prime t prime. This is the summation over m, and w of here n given m t, and then p m t and m prime t prime, and then minus w. Minus w here, you see x is sum over, so you need m here, and the initial state z is changed to be n, and then t here times p of z gets changed to n, and finally t y is the initial state. Okay, it's n prime t prime. So that's it. That's it. Okay, so this is the discrete version. Okay, so you have two versions of a matrix equation. Typically, actually, I think the second one is more dominant because of the nature of the jump process. Okay, so you often deal with discrete state space, but not always. Okay, you can have continuous valued. You can have continuous valued process that has discontinuous trajectory. It is possible. It is possible. For example, we just considered Brownian motion. We've been considering Brownian motion. So the size of the jump is Gaussian distributed. It is possible to have Cauchy distributed jump. So Cauchy distributed jump, in that case, you don't have finite moment, right? Finite moment. So for Cauchy distributed jump, you can have discontinuity in the sample path, even though the process takes values in a continuous space. So this is something that is kind of subtle. So we will perhaps we definitely will talk about the precise definition of continuity differentiability of stochastic process in our upcoming series for stochastic process for engineers. So here we've been making statements such as the Brownian motion is nowhere differentiable but continuous in a heuristic sense. Okay, but we never actually define it. Later on we will make that distinction. Okay, we'll make that definition precisely. So I'm just saying that jump process don't always have to be integer or discrete state space value, even though that's a very common scenario. Okay, it is possible for a continuous valued process to have discontinuous sample space, if that makes sense. Okay, so let me just draw the smaller rectangle and then drag it. So resize it. So this way it's easier to box equations. Because equations in this series are always seem to be quite big. So yeah, I'll finish up the random telegraph process. Okay, so from from the master's equation, we can write down dt p. Say if we start from A, okay, we start from A at t prime. This is the initial state. We don't know what the final state would be, right? So you need to consider two scenarios. But really, you only need to consider one. Here, N can be A and B, but you only need to consider B. Why? Because if you know PB of t, then PA of t is simply 1 minus that, right? Because you only have two possibilities. That's all you need. Okay, so let's write down the equation here. So now we have the you have W here. You need W. Let's write the sum explicitly. All right. So you have W of B given the initial state A. Actually, no. This is the summation index. The summation index M can be A and B. So let's use M equals A first. Okay. So WA T, right, times P of, here M is A, so PAT. The M prime is A. And M prime is A. And then T prime. Right? And that's it. That's the second term would be W. What's M? M is A. M is A, so W of A, given that here N is A, N is B. N is B, T. You see, it flips the arguments of W. So it's BA first and then AB times P of what? Times P of BT given AT prime. Okay, so this is the equation that you need if the initial state is A. That's all you need. You do not need to have P of AT anymore, as mentioned, due to normalization. So here, let's substitute the values. A to B rate is lambda. Minus, here, this is mu. P of B T given A T prime. Okay, let's do the other one. So now let's assume that the initial state is B. If the initial state is B at some time T prime, and your final state, we only need to consider A. That's all we need. All right. So there's that, and here using the master's equation, and by the way, some of you might wonder here in this summation, why do I only have one term? This is one term in the summation. This is a sigma notation. Why do I only have m equals A? Because here early on the left hand side, n is B. N is B. There's no such thing as WBB, so you just ignore it. All right. Okay. Next up, here, the second transition probability. This would be W of A given B T, P of B T given A T prime. Hang on, this should be B. My bad. The initial state is B. Initial state is B. Okay, B T prime, and then minus W of here. Swap the A and B, so B given A T times P of here you should have A T given. This is what? This is initial state is B T prime. Okay, now substitute. Here, B to A is mu. This is mu. All right, PBT given BT prime. And then minus A. Yeah. B, sorry, not A, but lambda. A to B is lambda. The rate from A to B is lambda. Assume this. Okay, constant. Okay, lambda times P of AT given BT prime. That's it. What's nice about this is that the system is already determined. You can write it as an ODE, system of ODE. So this is equivalent to here. You want to consider this as a vector. So this is d over dt of the vector here, P of BT AT prime, and then P of AT given BT prime. Okay, and now we can write it as a matrix. So here, this is a matrix. Okay, the matrix should be quite straightforward actually, because it's just you need to choose the constant correctly. Here, you want to write this as a linear combination of the same vector P B T given A T prime, P A T given B T prime. Okay, and let's look at the coefficients here. Well, here you have an AA. You see, that's an AA. So we need to do something about that. Okay, so let's need to do something about that. So we only consider transition. We only consider transition. So AA, no transition happens, so we can write it as lambda times 1 minus p bt, bt. So this way, the yeah, so you get a transition 1 minus p bt given a t prime minus mu p bt given a t prime. There's that. Okay, so now you can read off the coefficient, perhaps add some constants. We can do that as well. So the coefficient for p bt at prime, that's minus mu. So you put a minus mu here. And the coefficient for, hold on a second, they're the same. Are they the same? Doesn't seem right. That doesn't seem right. So here I'm using the initial state as A. The initial state is A. Okay, A should be here. And A should be here as well. Okay, hang on. Let me check my notes here. M prime T prime. Yeah, actually, you don't even need to write it as a system. You don't even need to write it as a system. This is already, the first equation is already closed. You can solve this. You can already solve the first one. You don't even need to, this is already decoupled. Actually simpler than I thought. Okay, so the first master equation is actually decoupled. So therefore, you have dt of the unknown function. Okay, and then plus lambda plus mu p of b t given a t prime equals lambda. And this is just the first order linear differential equation. With initial condition p b t given a t prime as sorry, the initial condition here is t prime is just 0. It's 0 because at initial time the state is A, is not B, so that probability is 0. So it's just a simple ODE. This is just an ODE, scalar ODE with the initial condition. This is solvable. Solution is elementary. Okay, so the solution should be, if we can spot it right away, what's the solution for that? This is the exponential growth, exponential decay function. But the initial condition should be 0. So it should grow like this. It should converge to a non-zero value. Should converge to a value, start from 0, it should converge to a value between 0 and 1. This is a solution behavior. This should be the solution behavior. I'm ignoring omitting the detail, okay? And speaking of which, yesterday I mentioned I'm going to make a bridge course on the fundamentals of ODE, including how to solve simple differential equation like this one, because we are now seeing a lot of content that has to assume ODE, like PDEs, SDEs, and control theory. So I think it makes sense and it pays to have a bridge course on that, so I don't have to always go back to, okay, how do you solve this? And I can just simply state the solution. But overall, that's the solution. You can solve this as the most basic ODE and get the solution. Okay, so that's a simple example of random telegraph process. And for the Fokker-Planck equation, well, for the Fokker-Planck equation, it's just W equals 0. There's no jump, only drift and diffusion. All motions are local. So that's special case 2, Fokker-Planck. Special case number 2 is the Fokker-Planck equation. Also known as the Kolmogorov forward equation. There's a backward equation as well. Backward and forward equation are both quite important. So this tells us the forward time evolution, Fokker-Planck and Kolmogorov forward equation. Okay, Kolmogorov derived both forward and backward. Fokker-Planck only derived the forward equation because this is more natural in physics. However, backward equation, backward PDEs in general is also useful. For example, in finance, you often have final condition instead of initial condition. Actually, one of the main problem is in finance is option pricing. Financial mathematics is option pricing. You know the value of the option at the expiry time, but you want to price it today, right? So you know the final value, but you want to derive the first value, the forward value, right? The initial value. And for that, you need a backward PDE. Okay, so we'll talk about Black-Scholes formula in a future episode, like a standalone episode. I just wanted to, my plan for the Black-Scholes is to do some PDE and then get the Black-Scholes rather simply, rather than deriving or developing the entire machinery of martingales from scratch, because Black-Scholes can be, first of all, Black-Scholes is very useful. Sorry, it's not super useful in practice. The formula itself is highly idealized, but the main idea is useful. Okay, the main idea, the no arbitrage pricing principle is useful. The Black-Scholes formula is more of a guideline anyway. So I wanted to develop the minimum machinery for the Black-Scholes, which we already have for the most part. I just need one more ingredient, Fourier transform, to get there. That seems like the shortest route at this point. But I digressed, okay? So I will just write down the Fokker-Planck equation. So Fokker-Planck equation is where you have W equals 0. No jump. No jump. All motions local. No, that's Fokker-Planck. So therefore, you just have you have a PDE. This is a second order parabolic PDE, of which heat equation is a special case. A is 0 and B is a constant. That's the heat equation. So Einstein's original description of the Brownian motion is the Fokker-Planck equation with zero drift and constant diffusion coefficient. So this is the Fokker-Planck equation. And just as an illustration, I haven't been reading chat much. Let me see if there's anything interesting in chat. Hang on, there's a bunch of questions. Hello, sir. If you don't mind, a question. In applied physics and engineering literature, I've seen CK equation for jump diffusion process called master equation. Is abuse of terminology. The thing is, you know, CK equation proper is an integral equation. Okay, so this is a logical structure here, right? So we started from the CK equation from the very beginning. This is just a law of total probability statement. That's it. And then you can derive so-called differential CK equation. A differential CK equation is, once again, not a universal term. It is a term used by Gardner. So basically, the idea is you want to derive the time evolution of the transition probability from the CK equation, which took us a lot of work, okay, including stating the hypothesis and do the calculus. The calculus itself is elementary. It's just keep tracking. This bookkeeping is annoying, okay? But now we finally have this equation that's the payoff here. Okay, so the master's equation is a special case of differential CK, as we argued. The master's equation is when you don't have the contributions from drift and diffusion, only jump. That's the master's equation. And this is usually what the master's equation mean in physics. Okay, master's equation is pretty standard terminology. And for Fokker-Planck equation is the differential CK equation without jump, only drift and diffusion. Okay, so I guess there's a little bit of a abuse of terminology. Okay, so in the CK equation, you should not see any derivatives. Cadillac isn't a term with I'm not sure. Okay, is Cadillac? Do you use the term Cadillac to describe trajectories? Or do you use that? Cadillac. Cadillac means I think it's continuous from the right, right? Limit from the left. Is that what it means? Okay, I've seen this term, Cadillac process, Cadillac function, Cadillac process. So right continuous with left limit. Yeah, so the CDF is a classic example. Cumulative distribution function must be Cadillac. Okay, and there's a space called Skorokhod space that allows you to define a metric over the space of Cadillac functions. But like, how do you describe things like Cauchy process? I was trying to use Cauchy process as an example that even though the space where the stochastic process takes values in is continuous, the process itself can still be continuous, can be discontinuous because the jump has infinite moment. That makes sense. So this is a sample path of Cauchy process. It's a Levy process, stable process, purely jump process. All right. Is it Cadillac though? Is the sample path Cadillac? I'm not quite sure. Actually, let's check. Let's Google. Let's AI. Okay. Our sample path of Cauchy process Cadillac. Okay, yes. The Cauchy process is a purely discontinuous Levy process with stationary independent increment. The path has no continuous component. Instead, they change via sudden jumps. Yeah. Cauchy process sample path. Okay. Hopefully, yeah, that's also something new for me. You said about finding option value line if it takes any asset which use and trade in time cycle. So do we need to find option value in that cycle? We know the premium or discount value. I see. Thank you, sir. Okay. Yeah. So we did not derive the backward equation today. We don't have time for that. Let's just say give a final example for Fokker-Planck. See how do you convert from stochastic differential equation to Fokker-Planck equation, go from SDE to PDE. Right? And it turns out to be actually surprisingly simple. Well, of course, with a lot of preparation work, right? You see, the final prize seems obvious, as we can see, but the foundation is quite deep. Right? So here, here's an example. So let's say we have a Ito SD. So Ito SD, by Ito SD we mean this. So you have dxi t equals ai of x x of t and t, okay, times dt. That's the deterministic part. Right? You already see this is a drift. This is already the drift. So no calculation needed. So k from 1 to m, you might have multiple sources of error terms. So that's I'm reading this as a system. Okay, okay. So x, let's say x of t is a stochastic process in Rd, and for I equals 1 all the way to d, you have this as dE, the sum of sigma ik volatility times x of t and t times dwk t. Okay, and wk's are assumed to be independent winner process. Okay, so this is etos SD, and just wanted to mention what this means. Okay, so because we never formally covered etos calculus, etos SD, etos integral in this series, but we did it on the stochastic differential equation series. So what this means is in the integral sense, so you have xit minus xi0. If you integrate on both sides, the first term, this is just a Riemann integral, assuming a is regular, smooth, and all those nice things, from 0 to t, a I x of s ds, plus on the right hand side you have integral with respect to the Brownian motion increment. So that's the stochastic integral. So this is the first one is just a regular Riemann integral. On the right you have a stochastic integral, and the stochastic integral is by default ambiguous. Okay, here the stochastic integral is by default ambiguous if the stochastic integral is interpreted in the etos sense, meaning you use the left end point as a sample point in the approximating sum. You get an etos integral, and from there the etos lemma follows. Okay, so here we're interpreting this as an etos integral. The other common choice is Stratonovich integral. In that case, you have a Stratonovich SDE. So this is etos. So the nice things about etos SDE is that you can immediately transform this into a Fokker-Planck equation. So you have these functions specified. Okay, given SD, given etos SD, you immediately have the vector A and the matrix, the diffusion matrix B, etos integral. Meaning of the SD. So given etos SD, we immediately can write down the Fokker-Planck equation. The Fokker-Planck equation, well, you simply have AI as a function of z and t earlier is just little ai. So that's just the drift. Okay, the drift in the Fokker-Planck equation is just the drift in the etos SD. Very easily. Okay, in the Fokker-Planck equation, this is A, and you have also the diffusion tensor Bij. Okay, so for Bij of z and t, you have an expression like this: k from 1 to m, sigma ik zt times sigma jk, sigma jk zt, sigma jk zt, and in a matrix form, the B matrix as a matrix this will be the sigma vector times sigma vector transpose. Let's see how this is done. So basically, we want to go back to the definition of big A and big B, right? So why? So let's just calculate the first moment of the increment. Okay, delta by the SDE, delta xi is AI zt. Okay, let's just say given the initial state, given x sub t equals z, okay, the increment in x over the next short time duration is you have the drift term plus a sum over k sigma ik zt times delta wk plus higher order terms in dt. Okay, higher order terms in dt. So if you've been following the stochastic series earlier, you would know delta wk is of order square root of delta t. So this is not a higher order term. In fact, this is a lower order term compared to delta t. This is O of square root of delta t. And by hot, we mean higher order terms of delta t. They can be ignored in the integral sense. But delta wk is not ignorable. Okay, so there you go. You have this situation, and then you just take the average. Because of wk has zero mean, boom. So expected value. So yeah, you just take the expected value. As a result, the expected value of delta xi, given the initial state is z, is just ai z t times delta t. So therefore, by definition, ai zt in the Fokker-Planck equation is just little ai zt. Done. All right, and for the second moment, you would need to calculate the product delta xi times delta xj, right? So you need that. Once again, conditioned at the initial condition z. In that situation, well, the drift term would be ignored, right? Because in the drift term, you have delta xi times delta xj. If you multiply the two, you end up the drift term product would be of order delta t squared, and that's a higher order term, so that's ignored. And then you have the cross term. The cross term would be delta t, okay, delta t times the increment in the Brownian motion, right? And that's also zero. Because of the mean of delta wk is zero. Not just because, oh, you have an order delta t times the order delta squared of t, that's a higher order term. No, not just that. It's actually because if you take the average, it's literally zero. So you only end up with the summation. So you only end up with the Brownian motion term. Okay, so for that you just get the sum over here. You just get the sum of you should have two summation, sum over k, sum over l, sigma ik, sigma jl, and then taking the moment of delta w k delta wl. but this is a Kronecker delta. This is a Kronecker delta KL due to independence assumption times delta t. So the double sum reduces to a single sum. You can write it as sum over k, sigma ik, sigma jk, yeah, and then delta t. So by definition, this is Bij. All right, so that's it. So you can convert freely between an Ito SDE and the Fokker-Planck equation. It's very simple. So which brings us a question: what if you use Stratonovich SDE? Right? There is a theorem that says you can convert a Stratonovich SDE into an equivalent Ito SDE, and from the Ito SDE you can write down the Fokker-Planck equation that way. But we won't have time to discuss it now. Okay, there is something called the Wong-Zaikai theorem. Wong-Zaikai theorem that allows us to convert Stratonovich SDE to Ito SDE. So really, in practice, it's kind of meaningless to say which calculus, Ito or Stratonovich, is superior. It's kind of meaningless to ask that question. The thing is, in practice, you always have an application in mind, and in the model formulation, you would typically choose Ito or Stratonovich. It tends to be the case that in finance, you almost choose Ito formulation, Ito integral, Ito SDE, due to the non-anticipating assumption, and also the efficient market hypothesis. That basically says the current market price includes all the information. But for physics, this is unnatural. Physicists tend to think in terms of the white noise correlation. White noise with delta correlated driving force in their differential equation. So Stratonovich interpretation, which is the midpoint rule for the stochastic integral, is more natural. So physicists typically write the stochastic differential equation as a Langevin equation, and then interpret it as Stratonovich SDE, and then to make use of stochastic calculus, for example, if they want to convert the Stratonovich SDE into a Fokker-Planck equation, they would first convert Stratonovich SDE into Ito SDE, and then use the method we just described to convert Ito SDE to a Fokker-Planck equation. Okay, and that'll be it for this mini-series for stochastic processes for physicists. I know we are severely lacking in the department of finding solutions and giving examples. Okay, so but that's just the unfortunate nature of the time constraint. Okay, I hope I will come back to this series in future to discuss more solution methods and see more examples. But now at least we have the fundamental principles. Okay, so we have an idea of what is going on. Okay, so this is the overarching perspective on stochastic processes. We mentioned earlier two perspectives. You can think of stochastic processes as family of realization, family of trajectories, or family of random variables. The first framework is reflected by stochastic differential equation, or Langevin's equation if you're a physicist. Okay, and the second one is the Fokker-Planck SDE, and now we see how they're connected. Okay, and this is only the beginning of the connection between SDE and PDE. Okay, so that's it. That's it for today. Thank you very much. We'll text you on Discord if you're free. Sure, go ahead. Yeah, so in chat, people have mentioned
So I'm new to finance and quant. Actually, just full disclosure, okay, full disclaimer. I'm not professional quant. Okay, I'm not professional quant. Um, so do not. If you're interested in professional quant's opinion of all of those things, you should probably contact people like Dimitri Blanco. I think that's his name on YouTube, as far as I know. Okay. Um, okay. And yeah, you can text me on Discord. Okay, I'll try my best. Uh, I'll try my best. So that's it for today. I really need to go. Okay, thank you very much for stopping by and listening to my stream. Okay, this has been a great experience for me. And as promised earlier, this will be all of this. Okay, will be uh, produced into a more polished and condensed videos. Okay, so now we have like two formats. I think that's kind of perhaps useful for some people. You have the long form and the short form. If you just want to like have a short, condensed video, there's that, uh, and there's also the more raw version of it. Okay, hopefully both will have their usage. All right, thank you very much, guys.